Hello, welcome to the introduction to the Bucknell COVID modeling that I've been doing. This is an epidemiological model that will help us understand what we might expect here on campus. Before we get into the model itself, it's important that we understand R, the reproductive number. In an infection, we can characterize the spread of the infection throughout the population by looking at how many individuals get infected from another individual. And so if R equals 1, that is each person who's infected infects one other person, then that original person will recover from the infection and someone else will get it. And the infection will spread across the population, but it won't ever reach a pandemic stage where it's growing across the population. On the other hand, if the reproductive number of the infection is greater than 1, in this example it's 2, this person here in the orange infects 2 other people, and that infection will then spread. It will increase in size, and now we have 2 people that will be infected, and they'll be able to infect 2 people. We can see this exponential growth more clearly if we just consider it happening from 1 person to 2 to 4 to 8 and so on until we have a huge number of infected people. You've probably seen this graphed in ways that show this exponential growth, where we have in blue here an exponential growth that's able to double every week in this example. Graph now shows exponential growth as a straight line. So you can see this blue graph is showing that the R equals 2 and the infection is growing exponentially. It goes up in a straight line on this particular graph, and that if R is less than 1, it will then go, have a downward slope, and the infection is being controlled. So what does this look like in our actual models? It's called an SEIR model, and these models are basically dividing the entire population into one of 4 bins, if you will. S means that you are susceptible, and almost everyone is going to start off in the S category in our models because they haven't been exposed or recovered from the infection. E is an exposed individual. This is someone who's been exposed to the pathogen. I is the infectious individuals. These are individuals capable of transmitting the disease. They will be spreading the disease to other S individuals if at the rate determined by the R that we're using in the model, the growth rate. The R in the SEIR model is referring to recovered or removed individuals. These are individuals that are no longer going to be susceptible to the infection, but they're also no longer spreading the infection. So we can think of this as a simple flow chart going from susceptible to exposed to infectious to recovered, and there are differential equations that are used to solve for the rates of change between these different categories. Here we can see a result of this SEIR model that I'll be using in order to demonstrate what it might look like here at Bucknell. This model was developed by several scientists at the University of Basel in Switzerland, and they have made this interactive model available online. This model is able to take in data from real reporting of, in this case, the United States, and we can see here in the orange points that we have the weekly cases of COVID-19 as reported across the entire United States. We also include weekly deaths in this model, and we can use this model to fit the reproductive number for this. And you can see in this scenario that in March, when the growth of the infection was exponential, it's a straight line there in March, we can see that the growth rate corresponded to an effective R of 4.5. At that point, sometime towards the end of March, we began taking effective intervention measures and mitigating the spread, and we were able to bring R down to about 1 across the entire United States. That varied, of course, a lot by different communities, but we were able to flatten the curve and reduce infection rates. This model is able to be adapted to different types of interventions, and you can see here I've modeled what's happened in the US where we had effective interventions throughout much of March and into June. And then after that, we had less effective interventions going on as we reopened the country. And finally, we're now reimposing some of those interventions. So this is just to remind you that we can look at this graph and see that the blue line represents the susceptible individuals. The orange represents exposed and infectious individuals. We can't tell those apart based on reporting data. And the green represents recovered individuals in this model. The important thing is that the interventions that we're imposing can stop susceptible individuals from being exposed, say by physical distancing, masking. It can also stop exposed individuals from becoming infectious if we're able to isolate someone who's been exposed and prevent them from spreading the disease to someone else. Now, they may still progress down this path, but if they do that in isolation, they don't spread the disease to someone else. And that's where quarantining and contact tracing plays a vital role. I'm going to now talk a little bit about the parameters that we're using to model these here on Bucknell. This is using what I've done to adapt this model from a countrywide SEIR model to local model. I've modeled a population of 4,700. That includes both students and the employees here at Bucknell, both faculty and staff. I've modeled an initial number of cases of 5. These are 5 people who arrive on campus or are already here who are infectious. This might be lower than that if we're able to very effectively screen, but it's probably a realistic assumption. And then we also have a model where we're importing cases onto campus 1 every 4 days on average. This is probably also realistic given the exposure of the community, people who might travel outside of the area. And so we have to include that in our model. Another important thing to note is that we're using an initial R of around 2.5. The model uses an average R of 2 to 3, and that's based on the latest CDC recommendations of what is an accurate spread of COVID-19 in the United States under today's conditions. These other parameters that you see here on this model aren't relevant to the modeling we're doing at Bucknell. Things like how many ICU beds we have. That's obviously not relevant to us here on campus. I have incorporated the demographics, the age demographics of the Bucknell campus using our best estimates of the age demographics of our staff and faculty and also of our students. I'm not including, by the way, students who have chosen to study 100% remote.